Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Today I'm going to talk about the Hypervisor Scheduler enhancement using OS hardware interactions. This work includes several projects I've done during my PhD study. So I'm going to start by talking about why resource management becomes more complicated today. So as you know, this software stack has been standard in the computer systems for decades. So in this stack, an operating system takes major responsibility for resource management. So in order to provide an applications with flexible and various services, an operating system usually supports wide interface, for example, a large number of system calls. So many sophisticated features have been proposed based on this semantically rich interface. However, as virtualization comes in, the things have changed in the resource management. So the hypervisor or VMM is another layer of resource managers underneath the operating systems. So the underlying hardware resources should be provided in a hierarchical manner. So this narrow interface, however, as opposed to the operating system, the VMM can access much less information recognized as a part of the OS hardware interaction. For example, privileged instructions or I/O operations. So this narrow interface makes the VMM secure, reliable, and OS independent. However, this limited access usually forces the VMM to provide the primitive resource management, such as file sharing. So the problem is that even though the hypervisor takes over the primary role of resource managers, it usually manages the underlying resources in a very primitive manner. So the many sophisticated OS mechanisms that are meant to be resource efficient may lose its power by underlying simple hypervisor. So among the virtualized resources, what I focused on is CPU resources because it can be shared over both time and space in a very fine-grained manner compared to other resources. And its scheduling has a direct impact on the application performance. And finally, the virtualization allows the diverse computing demands to be co-located. The CPU scheduling becomes much more challenging. So here's the general characteristics about how existing schedulers work. First of all, the OS and VMM schedulers work independently. So it makes the VMM OS independent. However, it also makes the semantic gap between them, where each operating system scheduler believes it's running on dedicated machine. However, underlying VMM scheduler makes them online and offline dynamically. Second, preserving inter-VM fairness is also the primary responsibility of the VMM scheduler because the most consolidated environments usually follow the multi-tenant nature or the pay-per-use model. So considering those characteristics, the most virtual machine monitors use the proportional CPU shared schedulers for performance isolation and the lightweight implementation. So such a proportional CPU shared scheduler considers each VM as a black box, like this figure, and try to focus on providing the VMs with the fair CPU bandwidth. So this workload-agnostic CPU scheduling is a dominant factor degrading the performance of each VM, inhibiting the cost-effective consolidation. So in order to solve this, we aim to enlighten the VMM scheduler about the computing demands of internal workloads by using OS hardware interactions. So by using existing OS hardware interaction without adding the additional interfaces to the operating system, we can keep the VMM still lightweight and OS independent without OS modification. So in order to achieve this goal...
What does it mean proportional sharing? This is a rate guarantee. What kind of latency guarantees? Are there any provided?
Actually,
what does it mean proportionally share?
Yeah, what I mean by proportional share is CPU bandwidth partitioning. So the latency is a kind of optimization of the proportional share scheduler, but what I mean by the proportional share scheduling is related to the bandwidth, the proportional bandwidth provisioning. So in order to achieve this goal, we have to address how to extract workload demands from limited information over OS hardware interactions. So this is our goal. So we try to focus on the two challenging workloads to be enlightened. The first is multi-threaded workloads, which is very prevalent in the multi-core systems, and they should be carefully scheduled because they are typically sensitive to the synchronization latency. And the other is the multitasking workloads, which mean the mixed workload in a single VM. So since the hypervisor scheduler aggregates the mixed workloads on a virtual CPU basis, so it is very challenging to properly differentiate such mixed workloads by using OS hardware interactions.
What kind of environment are you focused on? Is it an environment where there is heavy multiplexing of VMs to physical cores? Because in the public cloud environments, the pay-per-use environments, if I get a small VM, my VM is mapped to a single core, and then if I get a medium size, it's 2 cores. And so it's not obvious why, and when combined with the pay-per-use model, I don't know why. It's not obvious why all these enhancements are needed.
Actually, in our work, we consider it's a high consolidated environment. So actually, for the quality of service from the public cloud users, we can relieve the degree of consolidation ratio. But we always pursue the cost effectiveness. So we try to consolidate as many VMs as possible, and to solve the problem in terms of efficiency. So
for this to be useful and relevant, the number of VMs have to be twice the number of physical cores, an order of magnitude more. Just give me a sense of where.
Yes, but we don't assume any limitation about the consolidation. But in our evaluation, maybe in terms of the first work, we just twice the level of consolidation, the overcommitment. So I'm gonna present the demand-based coordinated scheduling, and for the multi-threaded workloads, and then the task-aware scheduling for multitasking workloads afterward. I'm gonna spend more time on the demand-based coordinated scheduling, which is the current and recent work. So let's get into the demand-based coordinated scheduling. So in this work, we try to focus on how to effectively consolidate multi-threaded workloads, which is very prevalent in the multi-core systems. So to begin with, let's look at the software trends in the multi-core era. First of all, applications are trying to increase their thread level parallelism in order to make the best use of increasing number of cores. For example, RMS, which is short for recognition mining synthesis, is usually highly multi-threaded and drawing attention as emerging killer applications today. So in such applications, synchronization has been well known as the greatest obstacle to the performance, limiting their parallelism. So in the user space, multiple threads communicate with each other by using a lock or barrier synchronization primitives. And also in OS layers, multiple kernel contexts running on each CPU may contend for the shared resources with synchronization such as spin locks. Another software trend is virtualization, which is widely used to consolidate multiple workloads on a single machine. So in a virtualized system like this figure, all synchronization activities in user and kernel spaces take place on the virtual CPUs, which are entirely controlled by underlying VMM scheduler. So the VMM layer should support synchronization-conscious coordination in order to efficiently consolidate multi-threaded workloads. So uncoordinated scheduling considers each vCPU as an independent entity, trying to maximize the CPU utilization. But on the other hand, the coordinated scheduling makes a decision based on sibling vCPUs that belong to the same VM. So as you can see from this case, uncoordinated scheduling could have a serious drawback caused by the contention between sibling vCPUs that are dependent on each other, thereby leading to inefficient synchronization performance, like this figure. So let me briefly...
So is this gang scheduling at the VMM, or is that something beyond that?
Yes, okay.
Is it gang scheduling at the VMM, or is it something beyond that?
So gang scheduling is kind of coordinated scheduling. And, let me briefly go over that. So I'm going to go over briefly prior efforts for coordinated scheduling. First of all, like you said, the coscheduling or gang scheduling provide the illusion of dedicated parallel machine by tightly synchronizing the execution of sibling vCPUs. But it's well known to be impractical because of CPU fragmentation problem. So in order to relieve this, relaxed coscheduling invented by VMware tried to loosely balance the execution time of the vCPU for the balanced execution. And similarly, the balanced scheduling simply allocates the sibling vCPUs to different physical CPU for the execution to be balanced. So those two schemes can achieve the high CPU utilization as well as the reasonable coordination. However, the coordination is not based on the actual synchronization demands. Finally, the selective coscheduling coschedules a certain group of relevant vCPUs for better coordination, but it currently relies on the user specification or guest OS support right now. So we need a new coordinated scheduling based on actual synchronization demands. So here's the overview of our demand-based coordinated scheduling. Normally, vCPUs are running without any coordination. However, when a vCPU expresses a demand of coscheduling for synchronization, corresponding vCPUs can be coscheduled on this demand. And also, when a vCPU makes a preemption attempt, but the running one wants to have more time slice for synchronization, we can simply delay this preemption by some extent. So in order to achieve this goal, one important question we have to address is how to identify such synchronization demands. In this work, we identify this demand in a non-intrusive design without any reliance on OS support or library support, only by using the OS hardware interactions. And we try to make our scheduler preserve the inter-VM fairness. Our coordination is independently carried out the time and space domains. In the time domain, the scheduler controls when to schedule vCPUs by manipulating the preemptive scheduling policy. So the coscheduling and the delayed preemption are decided in this domain. And the space domain, we can control the where to schedule by manipulating the physical CPU assignment policy. So I'm going to start the coordination in the time domain. But in this talk, let me focus on the kernel-level coordination demands, which has significant impact on the performance of most multi-threaded applications. But for the user-level coordination, you can check out the paper for more details. So first of all, we should be able to find out what types of synchronization really needs coordinated scheduling. So in general, busy waiting-based synchronization has been a well-known source of performance degradation because, like this figure, the CPUs can be unnecessarily occupied by busy waiting for offline vCPUs. So this problem is very serious, especially in the kernel space, because many operating systems make liberal use of busy waiting, such as spin locks, believing their vCPUs are totally dedicated to them. So regarding this issue, we have two important questions here. The first, when and where to demand such synchronization demands. And the second is how to identify coordination demands. So in order to find out the kernel level coordination demands, we did the experimental analysis by using the multi-threaded applications in the Parsec benchmark suite, which include emerging and diverse multi-threaded applications. And we can measure how CPU time spent in the kernel space could be changed or could be affected by uncoordinated scheduling. So as you can see here, in the case of a solo run without any consolidation or contention, there is almost no kernel time spent in every workload except one case of dedupe. However, in the case of co-running with another CPU-intensive VM, as you can see that the kernel time ratio becomes largely amplified by uncoordinated scheduling. That means the newly introduced kernel level contention. So in order to figure out where the kernel time is amplified, we did the kernel time breakdown by functions. So as you can see, the first source is a TLB shootdown, and the second is lock spinning. You can see that the two sources are dominant in the amplified kernel time, and the next question is, how can we identify each of them at the VMM layer by using the OS hardware interactions? First, let's look at the TLB shootdown. The TLB shootdown is a way of invalidating a TLB entry on a remote CPU. In this example, a thread on a CPU manipulates an entry of shared page table and invalidates the corresponding entry on the local TLB. And in order to ensure the consistent view of the shared page table, it requests to invalidate the corresponding entry on the remote CPU by sending an interprocessor interrupt, or IPI. From this point, the kernel on the source CPU starts busy waiting until all corresponding TLB entries are eventually invalidated. So such busy waiting for TLB synchronization is quite efficient in the native system because the IPI is very fast and the interrupt handler is a high priority. However, it could be ineffective in a virtualized system if the target vCPUs are not immediately scheduled. And it becomes even worse if the TLBs are synchronized in a broadcast or multicast manner. So we can identify this by means of TLB shootdown IPI, which is virtualized by VMM and used in the x86 Windows and Linux. And back to the amplified kernel time, the three applications that show the large increase in the the kernel time for TLB shootdown are also involved in the large traffic of TLB shootdown IPI. So based on our analysis, we can conclude for the TLB shootdown IPI, the sender and the receiver vCPUs can be co-scheduled in order to reduce the busy waiting for TLB synchronization. Next, let's look into the second source, lock spinning. The excessive lock spinning is typically caused by lock holder preemption problem called LHP, in which even a short critical section can be unpredictably prolonged by vCPU being preempted before releasing its spin lock, like this figure. So in order to figure out which spin lock is problematic, we did the lock spinning breakdown also. So as you can see, the red bar, the field text wait queue lock is a dominant source of lock spinning, accounting for 82% of total wait time. And including semaphore wait queue locks, 93% of total wait time is spent to protect the wait queue. So let's look at why and how the field text is involved in the excessive lock spinning. The field text is the Linux kernel support for the usual level synchronization, such as mutex and barrier. So in this example, the thread on vCPU2 has to wait until the mutex becomes available and request the kernel to insert itself to the wait queue and to be blocked. And then the thread on vCPU1 releases mutex and requests the kernel to wake up the thread on vCPU2 by sending a reschedule IPI while holding a spin lock. and the thread on a vCPU2 tries to wake up another thread after the critical section. So at this point, from our analysis, vCPU1 is frequently preempted before releasing its spin lock, and the vCPU2 starts busy waiting on the preempted lock. So the lock holder preemption actually happened. So why is this critical section prone to preemption? So as you know, initially the spin lock protected critical section is designed to be extremely short in practice. However, remote thread wake up is involved inside it. The critical section can be prolonged by expensive VMM intervention with the VM exit and entry for rescheduled IPI emulation. Even worse, more interventions are required to prepare for sending a single IPI. Furthermore, this can be repeated by iterative wake up. So as you can see here, we have no more short critical section here, so that the likelihood of preemption can be increased. And finally, this problem becomes very serious when the sibling vCPU is opened up on the same physical CPU as the waking one. So like this figure, because the lock holder preemption always happens in this case. So this problem is not only for mutex, but can be generalized to WakeQ locks. So in the Linux kernels, many general wake-up functions and the kernel semaphore or mutex unlock functions can suffer from this problem by preemptible or prolonged critical section. Also, based on this issue is very general based on the fact that multi-threaded workloads usually communicate with each other based on the WakeQs. So a rescheduled IPI can be used as a hint to delay the preemption of the sender vCPU until the WakeQ lock is finally released. So let's move on to the coordination in the space domain, regarding where to schedule. In the space domain, the balanced scheduling was proposed and verified in the recent Eurosys paper. This scheme is very simple. It just does by spreading the sibling vCPUs onto different physical CPUs without any coordination in the time domain. That means shifting all of the responsibility for time sharing to the default scheduler, the proportional CPU share scheduler. So as this figure shows, the situation where the sibling vCPUs are placed on the single physical CPU is so-called vCPU stacking. And the balanced scheduling is able to get rid of such vCPU stacking so that the likelihood of the coscheduling can be simply increased. However, one limitation here is that this scheme is effective only when global CPU loads are well balanced. But in practice, as you probably know, the VMs with the equal CPU shares can have the different number of vCPUs. For example, the SMP VM with the UPVM. And even in SMP VMs, the workloads can have the different thread level parallelism. For example, multi-threaded workloads plus the single-threaded workloads. Now also, the thread level parallelism can be changed even in the multi-threaded application, like this figure shows the varying CPU load as time progresses. So in this case, the vCPU shares or loads can be largely different from each other. So as you can see here, the balanced scheduling can make ineffective decision by placing the sibling vCPUs on the overloaded physical CPU in order to avoid the vCPU stacking. So we proposed an adaptive scheme named load-conscious balanced scheduling. So in this scheme, we just follow the balanced scheduling when the global CPU loads are well balanced. However, if the load becomes imbalanced, we just try to choose one of the underloaded physical CPUs in spite of vCPU stacking. However, the vCPU stacking can be appropriately handled by our coordination scheme, such as coscheduling and the delayed preemption in the time domain. So here's the evaluation. We implemented our scheduling scheme based on the Linux KVM hypervisor and the CFS scheduler. And in our evaluation, we first determined the effective time slice for the best performance of coscheduling and the delayed preemption. And in our sensitive analysis, the 500 microsecond, which is very short period, is most effective for most cases. And based on this, we evaluated performance improvement and discussed one of the OS re-engineering issues as an alternative. So I'm going to explain the last two evaluations in this talk. So in order to evaluate performance improvement, we consolidated 8 vCPU VM and 4 single vCPU VMs. And the execution time is normalized to the uncoordinated scheduling as a baseline. First of all, the balanced scheduling shown as the red bar shows the performance drop by placing the sibling vCPUs on the highly overloaded physical CPU in order to avoid vCPU stacking, like I mentioned. And as you can see, our load-conscious balanced scheduling, shown as green bar, resolved this problem completely. And regarding the coordination in the time domain, no performance impact take place for the non-synchronization intensive applications. However, for few text intensive applications, our delayed preemption, shown as the yellow bar, achieves the performance by up to 50% of 50% throughput. And for the TLB intensive applications, our coscheduling, shown as black bar, can achieve the 20 to 90% of performance improvement. So for TLB Shootdown IPI, you might agree that the IPI-driven coscheduling is definitely effective because the TLB Shootdown IPI is a very critical event for the performance. However, when it comes to the preemption-prone critical sections broken by the reschedule IPI, one might ask that this is kind of implementation problem in the Linux kernel. So it's not the Windows, right? So regarding this issue, in my opinion, all kernel codes are not all kernel codes are the virtualization friendly at this time. So our finding may drive the OS re-engineering in favor of virtualization. So we gave it a try to decouple the reschedule IPI transmission from the thread wake-up, like this figure. So by modifying the wake-up function and using the per CPU bmap, and we applied dispatch to the few text wake-up and few text requeue function, which are hotspot of the lockhold preemption in the Linux kernel. So as a result, as you can see from the rightmost, the yellow and black bars, the delayed reschedule IPI show the performance improvement similar to our delayed preemption. So we can conclude that the delayed reschedule IPI is very virtualization-friendly OS re-engineering by eliminating the root cause of the preemption-prone critical section.
Can you just question these bars for spacing? Is that a single instance, or are you doing multiple instances of that?
Oh, sorry.
For example, this FaceSim example, is that a single instance, or are you running that many times?
Yes, it's a single instance, and the consolidated other for consolidated with 4 single vCPU VMs. So and the single instance and with the 8 thread multi-thread. So the reason why I chose the FaceSim and the string cluster is that these two applications are very few text intensive. So the stress, the lockhold preemption caused by the few text is very intensive in 2 applications. So in summary, we found that the IPI is a very effective signal for coordinated scheduling based on the several useful findings. And also, the physical CPUs should be carefully assigned considering dynamic CPU load. However, scheduling alone is not a silver bullet because it cannot cover all types of synchronization demands, such as kernel spin lock contention that is not involved in the VMM intervention. So in the future, we plan to cooperate. We plan to make our scheduling scheme cooperate with other mechanisms like hardware-assisted the contention management and the power virtualization. So so I'm going to move on to the task-aware scheduling for multitasking.
So you talked about your solution essentially says, when you see this coordination demand, you should co-schedule people to get the efficiency. So why is co-scheduling the right thing to do rather than just descheduling the guy who's going to be sitting there spin locking in favor of the guy who he's actually waiting for? Why do they have to be actually scheduled at the same time?
You're asking that the reactive scheme, right? It's just spinning for a while and then the yield the physical CPU to another vCPU, right?
Well, so you're saying I have a guy who's waiting for someone else.
Yeah.
So I should schedule that guy he's waiting for to make sure that he's not just going there. Why not deschedule the guy who's waiting in favor of the guy who's being waited on instead of going for co-scheduling?
Yes, this is another solution. So for the relieving the contention problems. But so many power virtualization and the hardware-assisted virtualization take that kind of approach. By the descheduling the waiting vCPU is spinning vCPU and yielding the physical CPU to another, favoring another. So I think that this is kind of less effective than the co-scheduling because it comes at a cost of the busy waiting, even in spite of this is even though this is very small time. However, it's always busy waiting for a while, and then the yielding always generates the VMM intervention. It's just a VM exit. So the expensive VM exit is always required for this kind of yielding physical CPU. So we have a number in our paper. So the reactive scheme is less effective than the co-scheduling. Co-scheduling is more proactive. So in order to avoid that kind of problematic situations. So I'm going to move on to the task-aware scheduling. So while the first work addresses multi-threaded workloads, and task-aware VM scheduling is focused on the multitasking workloads. So which means the mixed workload in a single VM. This type of workload usually takes place in the virtual desktop infrastructure. So we try to focus on the I/O bound performance or the user interactive performance in this domain. So motivation behind this work is that the existing hypervisor schedulers are totally agnostic about tasks running inside the VM. So since the hypervisor scheduler regards a vCPU as an schedulable entity, so that the multiple thread and the mixed task on a single vCPU are aggregated as a single workload. So in this example, multiple vCPUs are waiting on the run queue sorted in the CPU fairness order. At this point, when an IO event is coming in, and the corresponding IO bound task might think that event is mine, and I'm latency sensitive to it. However, co-running CPU bound task has already exhausted its vCPU's time slice already, and making the vCPU to be placed at the tail of the run queue right now. So as a result, VMM should say that I see you only as a CPU-bound vCPU, even though this IO event is yours, and even with the lowest priority right now. And also, I don't even know if this event is destined for your IO-bound task. So I have no information about it. So at this time, I'm sorry not to schedule you immediately, even though it's yours. So for this reason, the IO-bound task inside the vCPU at the tail of the run queue could suffer from the poor IO responsiveness in that kind of mixed workload. So the task-aware VM scheduling enlightens the VMM about internal task by using lightweight inference based on OS hardware interactions. So this scheme allows the VMM to differentiate the mixed workloads, mixed tasks running on a single vCPU. So the task-aware VM scheduling has kind of history. The first proposal was focused on the I/O performance, and then extended with the driver VM specific scheduling. And the next proposal is a multimedia-friendly scheduling for video playback or 3D games for virtual desktop environments. And finally, as our ongoing work, I proposed the virtual asymmetry multiprocessor, which dynamically differentiate the power of the sibling vCPU in favor of interactive performance. So that I think that this might be the last work for the virtual desktop environments. So in this talk, I'm going to talk about the first proposal for I/O performance. So the ultimate goals of the task-aware VM scheduling is to track I/O boundness with the task granularity. And based on this, to improve the response time of I/O bound tasks. And finally, inter-VM fairness must not compromise by improving the I/O performance.
Quick clarification question. So you're saying one VM is actually running multiple tasks to a certain extent. Is it a realistic assumption? I mean, I could say, for example, that I can put, I don't know, a kind of one application that does one kind of tasks inside a VM, and perhaps we can differentiate based on a VM granularity rather than on a intra applications inside the VM. Is there a need to be that fine-grained?
Yes. Actually, this is a realistic questions I'm always getting. So, yes. So some might think that one application inside the one VM, so dedicated environments. But in this work, what I focused on is the virtual desktop environments. So the virtual machine is provided to single user, and the single user is always enjoying the multitasking inside the individual VM. So yes, the reason why I evaluated with the desktop workloads is our target of the work. So the following challenges should be addressed. The first of all, the I/O bound task can be identified from the black box VMs. And the second, we have to distinguish which I/O event is related to the I/O bound task. And finally, we have to partially boost the VM in order to selectively prioritize the I/O bound task out of CPU bound ones in order to improve the I/O responsiveness while preserving fairness. So first of all, let's look at how to identify I/O bound task. Like I mentioned, actually there is a very few the interactions available at the hypervisor. But luckily, the VMM can access the event of the address space switching because the updating an address space is required to be trapped to the VMM for memory virtualization. Even though this trap is not mandatory for the hardware-based memory virtualization, we can simply enable this trap by setting a control register simply. So by using this event, the Jones et al. Proposed the task tracking technique at the VMM layer based on the fact that an address space is associated with a specific task. So in this example, updating an address space generates a trap so that the VMM can identify a task is newly scheduled. And then switching another address space notifies the VMM of the descheduling of the previous task. So tracking these events, we can acquire the task time quantum of the task 1 as a clue of the task characteristic. So the task time quantum allows us to be able to use the traditional heuristic about I/O bound task characteristic. So as a common behavior, the I/O bound tasks usually have the short time quantum because they spend a lot of time the waiting for the I/O events. And also we can exploit that the many operating system usually gives the dispatch preference to the I/O bound task in response to an I/O event. So based on these two common knowledge, we just allow the VMM perform the statistical observations like this. So if a task is preemptively scheduled on its I/O event and runs during the short time quantum, and the I/O boundness is accumulated. However, the long time quantum is observed, some penalty is imposed. And then the I/O boundness goes beyond a certain threshold, and this task is regarded as I/O bound task. This is very simple, as you can see, and a lightweight approach. So this graph shows how our lightweight tracking works well in the mixture of real applications. So the top graph shows how the I/O bound grab task, shown as the red line, and the CPU bound compile task, shown as blue line, are well distinguished by our scheme. And the bottom graph shows that in the Windows operating systems, the GUI-based Acrobat reader is well classified from the CPU-intensive encoding task in this case. So this is how our lightweight and simple tracking techniques works well in the real-world applications. So now that we can identify the I/O bound task, we have to distinguish which I/O event is related to the I/O bound task. We use this correlation to determine which I/O event is latency sensitive. So the correlation allows the VMM to selectively boost the vCPU for latency sensitive I/O events, not the I/O events for the CPU bound ones. So in order to achieve this goal, we also devised the lightweight tracking in a best effort manner in order to keep the VMM lightweight and as simple as possible. So for the I/O event correlation, we consider two latency sensitive I/Os. The first is the block read, and the second is network packet reception. So in the case of block I/O, the correlation is relatively simple because the block I/O is always conducted in a request and response manner. So if a certain block is requested from the I/O bound task, we simply correlate its response event with the I/O bound task. But it is very simple, but like this figure, the block read request can be delayed by guest operating system, for example, I/O scheduler. So in this case, such a delayed request may not be associated with the currently running task. So we allow the VMM to inspect multiple tasks previously scheduled within a certain window. So in our sensitive analysis, by using the synthetic benchmark, this technique is very effective to keep track of the I/O event requesting from the I/O bound task with the little false positive. And for network I/O, the correlation should be different because network packet reception is asynchronous. So we used history-based prediction by monitoring if an I/O bound task is immediately woken up in response to a received packet. So this is also based on the common knowledge where the I/O bound task usually given dispatch preference by the operating system scheduler. So in order to improve the prediction, so we used the NB saturating counter for each destination port number, which is associated with the recipient task. So like this. So I think I'm sure that this figure reminds you of the branch predictor of CPU. So in our analysis, we also showed this structure is very lightweight to track the network packets from the I/O bound network applications. In the final stage, we want to selectively prioritize I/O bound task out of CPU bound ones in order to improve the responsiveness while preserving CPU fairness. And so in order to do this, I proposed the partial boosting, which allow the vCPU to be partially prioritized only while the IO-bound tasks are running. And also, it allows the vCPU to borrow future time slice as long as the fairness is preserved. So back to the early example. When an IO event is coming in, and VMM checks if this IO event for the IO-bound task in the VM3. And then initiate the partial boosting for VM3. And in this case, the IO-bound task can quickly handle the pending event and then the block for the next one. At this time, the VMM can detect the switching to the CPU-bound task. The partial boosting is immediately ended, get the vCPU back to the original place for the CPU fairness. So this is how we can improve the I/O responsiveness while preserving the CPU fairness as much as possible. So here's the evaluation results about the I/O performance with the workload mixes possibly in the virtual desktops. So we ran the multitasking workload in a VM, and this VM is co-running with 5 CPU-bound VMs. This is kind of the very high degree of consolidation assumption. So on the x-axis, the IO-bound task on the top, and the CPU-bound task is at the bottom. So as you can see here, the execution time is significantly reduced by our task-aware scheduling by up to about 50%. And the points inside each bar represent the CPU usage of each VM. So as you can see that the CPU fairness is not compromised, even though the I/O performance is significantly improved. So in summary, the virtualization enables multi-layer mixed workloads, which means mixed task on a mixed vCPUs. So as the virtual desktop infrastructure is drawing attention, so the multitasking workload is very typical and should be carefully handled for user experience. So the first task-aware VM scheduling is the first approach to handle such workloads, and by giving the VMM the notion of the task, and by using the lightweight inference based on the OS hardware interactions. So I'm going to end my talk by presenting the conclusions and my future work. In conclusion, we demonstrate the feasibility of how the simple hypervisors could be enlightened based on the limited information available at the VMM. And we don't require any modification or interfaces for operating system or applications, so thereby leading to the low cost of engineering and deployment. I believe that the Enlightened Hypervisor Scheduler is very crucial for the cost-effective consolidation. My future work is that the collaborative resource management in a holistic manner and assisted by well-defined interfaces. Although the non-intrusive solutions that I've really focused on during my work have their own benefits and attractive benefits. However, the computer system starts moving forward to the cross-layer interactions because, like this figure, the resource management have been more and more nested. So as you can see, the framework such as Hadoop and Android is usually placed between the applications and operating systems, and even worse than cluster-wide resource managers externally interact with the framework. So I just plan to make the standard interface, which is very compact and narrow between the resource management layers and across the OS VMM and the VMM and hardware. So this is my current focus and my related to my work. And also I just plan to make the framework or the cluster-wide resource managers to be aware of the virtualization ecosystems. So thank you for attention. I have to take questions or comments.
So your future work sounds very interesting. I guess I was wondering if you've given thought to whether this collaborative layered resource manager, will the challenges be different from other research work regarding resource management for data parallel frameworks? You use the example of Hadoop, and there are a bunch of resource managers, because in Hadoop you have these bunch of mappers and reducers and things like Spark from the Berkeley guys trying to figure out how Hadoop would work with some other framework. Will the challenges here be different?
Actually, what I try to focus on is just the virtualization related the resources. It's just, as you know, the virtualization makes the underlying resources very heterogeneous or dynamic, very in a time or the space things. So I think that the cluster-wide resource managers are not aware of underlying the stack. So what kind of VMM and the schedulers work underlying, and what kind of hardware is virtualized by the hypervisor. So I try to make the interface throughout the whole stacks, and ultimately I make the cluster-wide resource managers externally to be aware of the entire virtualized stack. So yeah, I try to focus more on the virtualization related problems, but other researchers are focused on the collaborative resource management like this. But I think that they overlook the virtualization and the virtualized environment, because it is kind of very complicated, and the hypervisor scheduler things is very complex.
So you had this for the I/O. You had this very lightweight detection of the I/O tasks and the correlation, and I guess that was cheap and works well. But I'm wondering why you even need to detect these things, since the task itself knows. The knowledge is somehow in the system. Could you, alternatively to making a heuristic-based detection, use this information, allow some signals to flow through, and get a much more reliable system out of it?
So why you're asking why the underlying hypervisor is estimating that kind of things? So I don't understand.
I was under the impression that your system was estimating which are the I/O intensive tasks that I should try to yank out.
Yeah.
If the task had a way of telling, I want to do I/O. It's in the code.
Yeah. This is my sure. So I think the most easiest thing, the intuitive thing is that the operating system or the task is just telling I'm I/O intensive, and just I'm really latency sensitive to the VMM, but it requires the interface, and I think that most people in the virtualized environment and virtualized resources, people really hate that adding some interface between OS and hypervisor, because it increases simply the trust computing base, and it's a very bad for the security. So by adding the well-defined interface to tell a hint for the I/O intensive task, it's kind of very intuitive. But in the current work, I try to do this by just estimating without any interface or just interaction between guest OS and hardware, the hypervisor. So that's a good comment. The power virtualization is also a good possible way of solving this problem.
So I guess we'll stop here. Let's thank the speaker. Thank you.